you are losing a lot of value if you can't make it. There's an enormous return on investment for any company that's paying a developer a reasonable developer wage and sends their developers here. I can't tell you how big of a mistake it is not to send someone to CppCon.
Hi, I'm Parsa Amini. Thank you for attending my talk. We are going to talk about leveraging assumptions to make your code run faster, or in other words, asserting your way to faster programs. A bit about myself. I got my PhD in computer science from LSU last December. I was working on HPX at LSU, which is the standard library for parallelism and concurrency. And I worked on adaptive load balancing of distributed HPX applications there. When I was about to defend my dissertation, I was also looking for work, and I knew I enjoy the vibrant atmosphere of the C++ community because C++ users care about the curve performance, overheads that they pay for, and productivity, obviously. And I was looking for ways to contribute, and I asked John Kalb, the CppCon conference chair, how do I make this happen? And at the same time, the chief software architect at Bloomberg, John Lakehouse, just had a presentation right before me, wanted to investigate how assumptions as a part of contracts impacts performance, which was because Herb Sutter had put forward a case study in a paper P2064R0, which we're going to talk about, where removing assumptions from an application actually made it run faster. How could this be? And I just happened to have the right skill set for the job. Jump forward, he started in April and been doing non-proprietary research. And today I have the privilege to deliver a CppCon talk on what I found. In this talk, you will see that if you are already using contract checking for correctness, you already have unrealized capital that you can extract by using assumptions, by assuming those checks that you use to enforce your contracts. That will make your code run faster on average. It will give you smaller binaries. Your code's compile time is not going to be affected, and if you're using contract checking for correctness, it won't cost any development efforts either. In case you're here looking for something very specific and want to know whether it's here or not, here's the outline of what I'm going to talk about. Can assumptions improve existing code? When the existing code that we're talking about is code that has matured over time and is well tested. Contracts generally exist to enhance the quality of the code. So such code probably makes use of contracts. And if you have contracts that have led to correct programs, you can capitalize on your contracts with assumptions to execute less code and get smaller binaries. In other words, with assumptions, you can get benefits at no extra development efforts. Benefits with no extra development efforts, how can that make sense? That is because contracts say, if you give me this, I'll give you this outcome. They streamline the development efforts, the development process, because they provide a medium for declaring your intent. And they prevent client misuse by checking for valid inputs that you pass to your functions. Not unit tests, we're specifically talking about contracts. Unit tests would check if your code produces the right results, produces the correct outcome with some valid input. That's a different purpose. We're talking about contracts, which make sure you always provide a valid input to your functions. A contract enforcement mechanism, checks the invalidity of the values you pass. That's what it does. And with it, contracts generally contracts come in exactly two flavors, narrow and wide. A wide contract has no preconditions. Any code that is correct, if you pass it, any input that is syntactically correct, if you pass it to your functions, is guaranteed to do something. It's well defined. No, you do not have to worry about undefined behavior in that case. In narrow contracts, puts some limits, and you now have a precondition on what valid input is. And that determines when a code is supposed to function properly as the developer intended. The contract itself is probably just the comments right above the function declaration in English. How do you enforce it? That's when the defensive checks come in. If you don't want to go out of contract, you check and act before you run the code to be in contract. The checks execute when the program runs, and if you want to test whether a program is working properly, you can decide, you can talk about the usefulness of a check. The checks are obviously redundant. That's by definition because the program is already supposed to be correct and not have errors. And what happens though is that as you develop your program, you keep running your program over and over, not testing actual execution of your program. If a program has been running a check for a very long time, and that check has detected no violations whatsoever, the value of this check is not the same after a while, because if it hasn't caught any violations after an adequate amount of time, depending on what you do, it is unlikely to do much anymore. It's unlikely to do much anymore. Its value has depreciated with regards to that one particular program. Take this square root function. We want it to return a double, and we do not expect it to work properly for a negative double value. That's the contract right above there in English. We enforce the contract by adding an assert statement that checks our precondition. Assert value is greater or equal to 0. Now, our contract says that calling this square root function with a negative value is undefined behavior, because the contract doesn't say that this function can work correctly with a negative value. And we have a check that can detect violations now. That's what the assertion is doing. The beneficiary of this check are the programs that call the square root function. If they pass a negative number, they'll encounter a violation. If they violate the precondition, the assertion is going to trigger, and the execution is going to stop, hopefully. Now we add a main function that calls our square root function. When it calls the square root function, it must provide a valid argument, obviously. This program takes the input from command line, and in this case, argc is not guaranteed to be 2, and argv1 can be negative. That's a defect. Why would you expect this program to always work correctly? You can't. This code is not mature, and if this code goes to production, it's going to contain a bug. So we need to validate argc and argv1 before we call the square root function. We do that, and if after enough time, which is subjective again and depends on what you do, 2 years, 3 months, 5 minutes, if the check does not catch any violations, we can consider this code mature. And then we can debate the value of enforcing this contract with regards to this particular program. What can we do now? Option 1, just keep checking. That's always an option. Say you have had this program that has had enough opportunities to violate the precondition, and you know for a fact that it has not because you've been auditing your code, and you know that no violations have been triggered. So now we have option 2. You can disable it for that particular program, and only for that particular program, because that's the only place you know you don't violate a precondition. And that's the only situation you can do that. If you don't know you're not violating any preconditions, doing anything other than checking the precondition is absolutely unreasonable. And if you know that you don't violate any preconditions and think it's reasonable to disable the checks, you are effectively assuming that the code is not violating, sorry, I misspoke, not test. You are assuming that the code is not violating any preconditions. If you can assume it, why not also let the compiler make that assumption? Why not let the compiler know it so it can assume it too? That's option 3. Give the compiler a chance to further optimize this correct code. So we have now 3 semantic choices: enforce, ignore, or assume the precondition. To recap, assuming a contract has meaning with regards to a particular program. Assuming something in a library doesn't make sense because you have no way of finding out if you violate your preconditions. We can do that for a program that has enforced that contract in production. It must have been in production, and only then we can consider assuming the precondition. With the contract checking semantics that we discussed, we can write one precondition check and choose the semantic we want. And take this trivial function that has an assert in it. It has a narrow contract that says this function works properly only when it receives a pointer that is not null. It doesn't do anything really. And printf swoops if you pass a null pointer to the, but the contract doesn't say that it must. It just does that though. If you compile this with enforcement semantic, you get all of this assembly for it. You have the precondition check, the compiler generates a test and jump instruction, and the code for the violation handler. The same branch that was used for the precondition check is also used for the if equals null pointer statement, and you have the code that calls printf. You get all of this with the enforcement semantic. What happens if you decide to not check the precondition, do nothing, ignore semantic? We would, in that case, still have an if statement, so the test and jump instructions stay, and the violation handling code goes away. You still have the code that does a printf, and the difference is now that if you violate the precondition with ignore semantic, you get a printf. You couldn't have gotten that before because you had violated the precondition. You would see an error message instead. Now that we get a printf, though, we have to ask, why did we stop checking if we can still violate the precondition? Or if we don't violate the precondition, what is the point of generating this printf? Either this is dead code or it's useless because we're supposed to check this and never encounter a violation. With assume semantic, let's say we know that the program that runs this code never calls this function when it's out of contract. If the compiler knows that it can assume that P is never a null pointer, then it would not bother generating any code that checks if the pointer is null anymore. The only thing that will be left of this function is just the return statement. It won't do anything anymore, and that's exactly correct. This function was supposed to do nothing if it was given correct input. Taking advantage of assume semantics is exciting because we can expect assumptions to enable the compiler to optimize better. But that's only meaningful if we don't have a bug in our code. If an assumed contract is violated, in words of John Lakos, all bets are off. If a precondition that was previously checked gets violated, and you chose not to enforce the checks anymore, you're responsible and you have no recourse, and you're left with undefined behavior. Next thing I have to mention is that one class of bugs that can get overlooked are wide contracts in narrow clothing. That's a made-up term, but let's describe them. What are wide contracts in narrow clothing? What if you have wide contracts that are marked as narrow contracts? What if we have a check for invalid inputs, but also have code that separately checks and handles corner cases? If you let the check catch violations, you'll catch the violations. Genius. But if you check that you won't violate the precondition, then what's the if statements? Oh, I thought I had been pointing at this the whole time. Then what is the point of the if statement? You claim that the function has a narrow contract, and you enforce it with the check. What purpose does the if statement serve? Nothing. If you disable the check, your program may work correct. You had an if statement there. But there was a precondition violated. Now you're handling the violation without ever knowing. You have no way of detecting it, which defeats the purpose of the check. And you have a defective program. If you violate the precondition and also assume, then you're also falsely telling the compiler that you know that the violation does not happen. The compiler considers that information and takes out anything it can reason is unreachable. And if you had a bug in your code and falsely told the compiler it can assume a precondition that you didn't know or knew is false, then the consequences can be outrageous. Got the dragon stuck in the ceiling fan. What is this error message saying? What am I supposed to do with it? And which one is the stuck? Can't say. If that's too abstract and doesn't make enough sense, then this example from Herbstadter's paper might improve things. Say you have a macro called deassert that checks for violations in debug mode and assumes the predicates in retail mode. You have a do something function that takes an integer that is never supposed to be 0 and has a deassert in it. Its developers, the users of this function could notice violations if they ran it in debug. And because of that if, they expected that this code would return -1 when x is 0 in retail mode. Except they never actually let the check catch violations in retail mode. They never encountered that. So they instead experienced what they described as strange crashes. This code has always had a bug without assuming the predicates. And when you assume it, it's not exactly making things any better. This code essentially suffers from two types of cancer. Two bad decisions in this code. One is that the deasserts never had the opportunity to catch a violation in retail and was assumed. That's the first one. The second one is that someone wrote code that is only meaningful when the check gets violated. We're losing cabin pressure, and we're going to serve tea in a few minutes. What's the point? What is the state of language support for contracts? It is not a part of the C++ language yet. And just for reference, here's a list of papers on contracts that you could take a look at if you wish. Same deal with assumptions, not a part of the language yet. The committee has considered contracts and assumptions. And here's the list of papers that you could look at for reference. The C++ language does not offer contracts or assumptions, but they're very basic features, and the language not supporting assumptions or contracts does not mean that users don't need or try to use them. All major C++ compilers provide intrinsic functions for replicating something like assumptions. Their use is actually common in performance-sensitive code, and it's a shortcoming of the C++ language that it doesn't support it. As for contracts, if you want contracts, C-style asserts already exist. You can use them to enforce your contracts. The caveat is that they're asserts, they're macros, and they're not a structured C++. They're not structured C++ syntax. And but if you want actual contract implementations, either you can wait for GCC 12. Next April, I think, is what's going to be released, which plans to implement contracts. Otherwise, you can check out the GCC contracts branch today. It's also on Godbolt. There's also a Clang implementation that seems to have not been active recently, and I haven't gone to test it. What about the implementation? What's the state of implementation of contracts and assumptions? You can implement contract checks with certs and control it already. You can control what happens to your assertions by defining or undefining the ndebug macro, define ndebug if you want to ignore your asserts. And if you want assumptions, you can adapt your C-style asserts to some preconditions. It's not difficult to do that. You can implement assume semantic by using the compiler intrinsic for each platform. That's exactly what GNU-lib's Assure macro does. That's a C library. GSL and BDE do that in C++. Or the C++ libraries that do that. So far we talked about defensive checks, the three contract checking semantics that were check, ignore, and assume, enforce, ignore, and assume. We talked about wide contracts and narrow clothing, state of the language support, compiler support, and library implementations of contracts with and without assumptions. And now it's time to move on to talking about our method. Using assumptions is a no-brainer if they're cheap to adopt and improve some measurable characteristic, but we do need to know if that actually happens. We need measurable performance metrics. In our method, we consider these metrics for the impacts on the development process. We need to know what does it take to assume preconditions. We need to know if the compile time is affected. And for memory impacts, we use the Kruger metric. We check if the memory high watermark changes. So we can tell if we actually need more memory to compile the same code. To assess the runtime impact, we need to see if the runtime changes for some program between ignored and assumed contract checking mode. Between ignored and assumed contract checking semantics. And we can additionally also check hardware performance counters if we could find a discrepancy. And lastly, we could compare the generated code sizes to see how assumptions can impact your code. A case study that would show an assumption that would show assumptions help must convincingly demonstrate at least one metric that improves, one performance metric that improves. And we also would like to have a case that is easy to reproduce and minimal, easy to reproduce experiments to strengthen the case. Work that considers assumptions performance impact is limited to Herb Sutter's and mine as far as I can tell. Herb's is already published in P2064R0, and mine will hopefully soon be in P2421. Herb's paper contains a case study where an application's runtime is affected by assumptions. It actually runs 1 to 2% faster without assumptions. We don't have access to that code, so we can't exactly assess that claim. So its mention is in P2064 is all we have from that experiment. In my case, I'm interested in making the method publicly available and the experiment reproducible. That limits the relevant pool of applications and the programs that I've had access to are BDE's tests and a bunch of micro benchmarks that I myself developed based on comparing the changes in the generated assembly of all of the functions across the entire BDE code base that see a change between the ignored and assumed mode. To recap, we talked about the relevant performance metrics that indicate an impact by assumptions. We also talked about the applications that we tested. Just briefly, I'll go through Herb's paper, the parts that I found interesting. Herb's paper mentions an application that had assumptions in it, and he also had an example code that I presented earlier with that had the deassert in it, and he also explains that why that example was defective, and how use of assumptions. He makes a case that use of assumptions conceals their code's defects further, to the extent that removing assumptions made their code 1 to 2% faster without resolving the bugs. That's one thing. The second interesting fact about this, second interesting thing to me is that he suggests that having assumptions may impose some overhead for the compilation time or the memory that's consumed for during compile time. In our case, we use the BDE libraries to study the impact of assumptions. If you're wondering what BDE is an acronym for Bloomberg's development environments. It's also basic development environments, or even just BDE development environments, depending on who you talk to. You get different expansions. BDE libraries include an implementation of the standard library. And for us, it's a good target and low-hanging fruit to study the impact of assumptions, because for one, it already exists. They are in well-written and well-tested idiomatic C++. They implement contracts. It also has experimental support for assuming precondition checks. That makes things a bit easier. Low-hanging fruit. And lastly, the BDE libraries are a large set of libraries. BDE libraries are large libraries that are already instrumented with contracts and are maintained and have been extensively in production since 2004 with contracts. The idea of using them the idea of this study is to assess the impact of assuming the many precondition checks in BDE library on a systemic level and see how that impacts performance. How does contract checking in BDE work? We had 3 contract checking semantics that we discussed: enforcing, ignoring, or assuming preconditions. In BDE, you can control that with the following macros: BSLS assert asserts, assert disabled, or assert assume. How does BSLS assert sort works? It expands. It's a macro that expands to either good old-fashioned assertions or a violation handling mechanism. If you want to ignore contracts, ignore precondition checks, not contracts. If you want to ignore a precondition check, you just expand to nothing. And if you want to assume a contract, you expand them to the compiler intrinsic of the specific platform your code is going to run on. So we discussed P2064, which is published, and mentioned its results. We discussed what makes BDE libraries a good target to experiment on and what is available to experiment on. And we now move on to the results of our experiment on BDE. Our experimenting subjects were BDE's own tests and a bunch of micro benchmarks that we developed based on. I'll explain that again soon. We did our experimenting on an Intel Ivy Lake machine with Clang 1201 in C++17 mode. This slide is mostly for reference. So how does BDE go about contract checking? It's not either all or none. BDE has 3 levels of assertions. BSLS assert is the one that is everywhere. There is BSLS assert safe, which is used when some check is likely to be expensive and shouldn't be run as often. And BDE assert opt, which is for checks that are critical for correctness. how many assertions are present in our code. Here's a breakdown of how many assertions of each type are present in the code that we work on. We only count the assertions that were considered by the compiler during compilation on our platform. The plot on the left is the breakdown of assertions in BDE libraries. The one on the right is in the entire code, including BDE and its test together. The reason I've separated them is because what happens in the test may not say much about other programs that use the BDE libraries, but the one on the right is still interesting because our experiments include building and running the BDE test. So what's in them is also interesting. As I said before, most asserts were plain BSLS asserts, 5,000 of them in the BDE code against 2,000, less than 2,000, fewer than 2,000 BSLS assert safes and fewer than 200 BSLS assert opts. About 70% of the assertions are BSLS assert, essentially. When we built BDE with ignored and assumed semantics, we did not observe a difference in compile time or compiler high water memory mark. With a confidence interval of 95%, I forgot to put that there. But we did get smaller binaries. We got a bit of space saving overall. And what was surprising, though, was that we saw some sharp increases in some of the compiled function sizes. But the decreases were more frequent. Most changes are very small, but the distribution of changes is positively skewed. So the machine code for many more functions actually show a shrink in size with assumed semantic compared to ignored. And the code size increases we saw were mostly because of loop unrolling optimizations. This function is one case, except the function is massive. So here's a simplified reproduction of the two effects at work in one case, in one loop unrolling case. One effect is that the assumption lets the compiler predict the size of the loop, so it unrolls it. That in itself may not result in more instructions, except the second effect is because there's an if condition, there's an if statement in the loop that's inside the loop that the compiler can now see through. So you end up with more lines of assembly. The code size actually gets inflated because of that. The code size decreases we saw were mostly dead code removed. One example is this one. Again, it's a massive function. Here you can look at the def for what that looks like with a specific function. But to show you a simplified reproduction of what that example is, effectively, it's a branch that compiler just is able to identify as dead code and remove. Runtime performance. We ran the tests that the BDE libraries come with and saw no performance degradation within a confidence interval of 95%. And it wasn't convincing, so we also decided to take a look at individual functions that were affected from what we discovered by comparing the function sizes, and develop micro-benchmarks to see how those functions perform differently. Again, we saw no performance degradation with the same parameters, except one micro-benchmark consistently is able to show a performance improvement. It's a swap overload that gains performance from an unrolled loop. In short, at the effective development cost of toggling a compiler flag, we got a tiny bit of performance improvement, got no performance degradation, got smaller generated binaries, and didn't have to wait longer or use more resources to compile their code. Turning off checks. Conclusions of this presentation would be turning off checks, but being afraid of assuming is the nonsensical because you know your code. If you know your code is buggy, if you don't trust your code enough, and still wish to disable the checks, what do you expect? Until you know there is no defects, there's no point in turning the checks off. You're inviting bugs otherwise. To recap, I told you what we found and told you that the compile process does not take longer, require more memory. We showed the numerous functions, generated codes increased in size, but that overall we saved some space, and that we have not seen any code that actually runs slower. But some codes can and do run faster. That's not all. What's left is we need results from real applications. These were tests and micro benchmarks. That is still something to do, and obviously I still have to finish the paper. And again, since the results of this study are to be public, I need to complete what's left of publishing the results. I've put I put up the disassemblies and the diffs and some crude decompilation of what the differences are between the ignored and assumed modes in BDE, what the instructions, and plenty more is still left to do. And the takeaways. If you have defensive checks in your code, I believe, in addition to enhancing the quality of your code that you get, you can also get collateral benefits in terms of performance. The next one is that we have new data that shows correct code doesn't run slower with assumptions. And we also have data, our data also shows that correct code can become faster and smaller at no extra development efforts. And because of all of this, or at least I would very much like to see contracts with assumptions to be in C++ 23.